What's up everybody? My name is Aaron and today we're going to learn about the citric acid cycle, aka the Krebs cycle, aka a million other names, but we're going to call it the citric acid cycle. So to start out with the citric acid cycle, I'm going to give you some brief overview of some important things to give you some background knowledge. This is probably a review for a lot of you, but this is glucose, a wonderful hexagonal glucose sugar. Each one of these points represents a carbon, so 6 carbons in glucose. Okay, so you have a 6-carbon glucose, we break the bonds, and that is what helps us drive cellular respiration and eventually create ATP, which is our body's energy source to do all kinds of stuff. So, this is the first part where we have 6 carbons from glucose. It's called glycolysis. This is a lot more complicated. We're just going to go super simple because we want to talk about citric acid. So in glycolysis, we form 2 ATPs and we form 2 NADHs. And so these NADHs are going to be used later. Those are our high energy intermediates that help drive the electron transport chain, which is where the majority of our ATP is made. And so I'm writing out these ATP, but really the ATP made in glycolysis and the citric acid cycle are just like a fraction of the total ATP that each molecule of glucose makes. Okay, so glycolysis, it cleaves glucose into 2 pyruvate. So pyruvate's a 3-carbon sugar. Pyruvate goes into something called pyruvate oxidation, which has a bunch of little steps, which is really fun. We're not going to talk about. Essentially, coenzyme A comes in and CO2 comes out. So coenzyme A attaches to pyruvate and we lose a carbon that gets released as CO2, and we're also creating more NADH. And so our final product is acetyl-CoA, which helps us start the citric acid cycle. Okay, so this is a simplification of the citric acid cycle. We'll go into the nitty-gritty here in a minute, but just an overview. Citric acid cycle starts with oxaloacetate, which is a mouthful. We have our acetyl-CoA comes in. Oxaloacetate is a 4-carbon molecule. Acetyl-CoA is a 2-carbon molecule, forms a 6-carbon molecule. It goes around the ring, and we're creating our high energy intermediates, NADH and FADH2, along with a little bit of ATP. And so for each molecule of glucose, it drives 2 turns of the citric acid cycle. Okay, so this looks kind of overwhelming, but this is the citric acid cycle. Each one of these has molecular structures that I didn't draw out to make it a little more simple. So essentially, where we started out with last time, oxaloacetate is the beginning of the citric acid cycle. Our acetyl-CoA comes in, donates its carbons to oxaloacetate, and we form citrate, and coenzyme A is released to be recycled. So citrate is a 6-carbon molecule. Aconitase is its intermediate. So citrate reacts with aconitase, forms isocitrate. Isocitrate reacts with isocitrate dehydrogenase, which in the process of doing that, it cleaves off a carbon, which is released as CO2, and NADH comes in and is reduced to form NADH. And so we're starting to make our high energy intermediates. So the next one is alpha-ketoglutarate. Alpha-ketoglutarate is a 5-carbon molecule. Alpha-ketoglutarate reacts with alpha-ketoglutarate dehydrogenase complex. You can say that 5 times fast. And in that process, we're again taking NAD+, creating NADH, and releasing a carbon as CO2. Our next one is succinyl-CoA or succinyl-CoA, depending on how sciencey you are. So succinyl-CoA is our 4-carbon molecule, and it'll remain a 4-carbon molecule throughout the rest of the citric acid cycle. But we're going to go through the rest of the steps because it's more fun that way. So succinyl-CoA reacts with succinyl-CoA synthetase. to form succinate. In the process, this is fun, you actually get a DP and a free phosphate that forms ATP, and that coenzyme A is released and recycled. So we're starting to form ATP. This is the lone ATP that the citric acid forms each time it turns around. So succinate goes through the succinate dehydrogenase complex, and we form FADH2, which is our other high energy intermediate. You're actually going to see succinate in another pathway in electron transport. So after FADH2 is formed, you get fumarate. Fumarate reacts with fumarase and water to form malate. Malate goes through malate dehydrogenase, and we get another NADH coming out there. And that brings us back to oxaloacetate, which is our starting point. And then oxaloacetate can react with citrate synthase and acetyl-CoA to form citrate, and that's why it's called the citric acid cycle, because it goes around and around over again. So the important thing to remember, I guess all of it, if you're a biochemistry person, it's important to know all of it. But for everyone else in the world, NADH and FADH2 are your reduced high energy intermediates that donate their electrons to the electron transport chain and help drive the production of ATP. Because if we were just getting ATP from here and the two created in glycolysis, it wouldn't be enough to run body function. So yeah, that's the citric acid cycle in a nutshell. Okay, so in summary, this is the overall reaction of the citric acid cycle. So we have 2 acetyl-CoA plus 6 NAD plus 2 FAD plus 2 ADP plus 2 free phosphates gives us 4 CO2, 6 NADH, 6 free hydrogens plus 2 FADH2 plus 2 ATP, and that is the net reactants and products of the citric acid cycle.